and it has built-in design rule checks that automate design manual checking for layout. So once again, it reduces the manual design time from a few hours to minutes because these checks run very quickly. It's got SI checks, power integrity checks, and EMI checks built in, and high voltage safety checks as well that we're going to talk about today. HyperLynx DRC also has its own script writing and debugging environment, so you can write your own custom checks and include that into the tool. So whatever your PCB review process is, HyperLynx DRC can automate it. And a lot of the stuff out of the box will cover the checks you run today that are manual checks. Right now, there's 40 plus built-in DRCs with editable parameters, so you can take your datasheet or app note, whatever it is that you're trying to verify, and put those values in, and it'll automatically check it for you. Some examples are high-speed traces crossing gaps, where a high-speed signal will see an impedance change on that gap in the power planes. It'll cause a reflection of that signal. So that's something where you'd manually need to check high-speed nets in the design, layer by layer, net by net. Decoupling capacitor placement, saying if the voltage on the capacitor is the proper voltage to decouple the IC power pin and if it's close enough within the proper distance. Return path changes for signals, crosstalk checks, impedance checks, differential pair phase matching, all the things that are hard to check for manually. Another thing that's very tedious to check for is high voltage safety, where high voltage energy will creep from a high voltage object along the surface of the PCB and affect other objects on the board. So we call this the creepage distance. It's like the minimum distance that objects should be spaced apart to not get that high voltage safety issue. And the way that customers and designers check for this today are they use IEC standards to validate the minimum creepage distance for their prototype board. There's different standards for power electronic equipment or medical equipment or IT equipment or electrical cables. So what we've done is we've actually automated this process and embedded these IEC standards into our HyperLynx DRCs. And we're going to show that in our demo today. So this is a problem that's very tedious on the order of it takes days of engineering time to check for. It's a very simple process in that it's easy to calculate for. It's a simple formula. If depending on the material of the object and the pollution degree of your environment, there's a minimum distance that you have to know. But to check for this manually takes days of time because there's thousands of nets or thousands of objects on the board that are susceptible to the high voltage radiation. So here we're actually going to use HyperLynx DRC to do a same layer check. It's just a simple creepage check. On the right in dark khaki, we've got a 200 volt power net, and you can see the minimum distance that it's affecting that 1.5 volt net that's nearby is it's too close. So we're getting it flagged in red and it's saying, okay, here's the creepage distance, and it calculates it for you automatically. That's just a simple same layer check, but the real benefit of these rules are to use the 3D creepage engine to check multiple layers on the board, top side of the board, bottom side of the board, and to check for the surrounding floating metal with the built-in IEC standards embedded. So in this check, we have that lime green victim net that's farther away, and it actually is, very far from that 200 volt aggressor net. It's so far that the creepage distance, should be fine. But the surrounding metal around that board, the dark green nets, are an extension of that victim. So in actuality, the creepage distance is very, very small, on the order of 1 millimeter instead of 50 or 500 mils. So we're looking at something that you'd have to check for manually and is very, very hard to spot sometimes. Creepage distance is different than clearance distance because it mines an air gap. So because it creeps along the surface of the board, if there's a slot or a hole in the board, like in this example, the creepage distance has to walk around that. So HyperLynx DRC can read all these holes in the board and can analyze them automatically for you when it might be a little trickier to know the actual full distance there. Now HyperLynx DRC, just like Validate, works on any layout. So you can work in Cadence or Zukin or Altium or any ODB++ data. But the benefit of using a TensorFlow is that it's integrated into our layout tool, Expedition Layout. So here we're using Expedition to run the checks again in their environment in the Expedition Layout GUI. So you're not learning anything new. You're using the Hazard Explorer to report the violations. And in this case, we have a high voltage 100 volt net aggressor on top side of the board. And you can see it's going through that slot in the board to the bottom side of the board and affecting an object on the bottom. So it's very tedious to check this way for the creepage as well in the high voltage. Another example is the board edge. So we have that khaki 100-volt trace on the top side of the board, and we can see that it's actually creeping around the edge of the board and affecting a net on the bottom side of the board. So creepage and clearance are very easy to understand issues. There's a high voltage issue, it's creeping to other nets and affecting and radiating to other objects on the board. But to check for this manually is very, very, very tedious. So HyperLynx DRC automates that for our users. And since we're in the Expedition layout environment, we have the ability to make and move these nets automatically because we're already there in the environment for layout.